I suppose we're nearly there. Welcome back, folks. Before we get started, any questions you folks would like to discuss about the calculus we've been doing so far? Hard problems out of the homework? Really anything at all is fair game for questions at the start of class. Okay, well, maybe a couple announcements before we get started in finishing section 8.3. First announcement is one of our fellow students in the class has graciously been recording the lectures and uploading them to YouTube. So if you'd like an extra resource to revisit lectures, then you can go to the very top of the Moodle course, go to class lectures, and it'll take you to a YouTube page where, well, there's already a lot of stuff there. So thanks to Christian for providing those YouTube videos. You can like and subscribe, but you don't have to. They're just there for reference. Any questions about that so far? Okay. Also, other announcements that we have are, we do have the federal holiday coming up next week. The week after that will be midterm week, and your course grade that you saw in your first exam will just be updated with the new homework problems that have been graded. The week after that is exam 2 week, so there's something going every week so far. Because of the sick day, we may not cover all the way to 11.3. It just depends on where we end up. So far it's looking like we'll end up a definite at 11.2. And as we get closer and closer, we may revise this list to more accurately reflect the content for that exam. And as we get closer, we're still a ways off. A new sample exam will be provided, just like before. Then the week after that is last day to withdraw from the semester. The week after that will be spring break. And then we'll be pretty much nearly done with the course. We'll still have the third exam to get through. But any questions about that so far? Okay, so the assignment that's going to be due on Thursday, which is Valentine's Day, is kind of a relaxing assignment. It'll just involve those 5 problems. There are slightly tougher problems, mainly getting through the algebra. Then, for the upcoming assignment that we're building, it'll include 8.2 and 8.3 for sure, but again, we're off by a single day, so we may not quite get to 9.1. I'll have that completely updated after today when we get a better idea of where we're at. So that's the announcement so far. Any questions then before we get started? Okay, I guess I have a question. A good question is, the section of the title, 8.3, centers of mass and centroids, we still haven't done anything about centroids. So the question is, what do we mean about centroids specifically? And the short answer is, centroids are just centers of mass with a specific context. And that context is, suppose for example that you had some kind of plate. It's going to have a uniform thickness and a uniform density rho. We didn't say what the thickness was because it does not enter into the calculation. Then we look at just the top view of the plate so that we're only looking at a 2-dimensional view of it. Further things that we want to assume are the curves that are generating this plate are continuous curves. So this curve here, f of x, must be continuous. We have further curves. We still call these curves even though they're straight line segments, which is kind of weird. They're curves with no curvature. Y equals 0 would be the bottom curve here. X equals a are the vertical line segments here to here and here to here. So altogether, just visualize some kind of strange looking plate, uniform density, the exact same thickness all throughout. And by centroids, what we're trying to do is find the center of mass really of this plate. So we can imagine if we were to eyeball this, the center of mass, there's halfway point is here. It looks like there's slightly more mass to the left. So my x-coordinate for the centroid might be slightly to the left somewhere. So along that line segment, I could put a point that it may bounce on. Might not be fully accurate. We also need a y-coordinate. If we were to estimate the y-coordinate, say from here to here, about halfway is this value. It looks like there's a lot of area below, so I'd probably say maybe there, if I had to completely visually estimate where the y coordinate of the center of mass, or centroid is, of that plate, visually I would place it in that position. And possibly it's not going to balance, more likely than not. So what we'd like to do is calculate the coordinates exactly for the center of mass. To do that, we have to use the information that we've been exploring from the one-dimensional case. In the one-dimensional case, we're really just looking at the formula for an average. The formula for the average has a nice intuitive description of finding a center of mass really, or deciding where the fulcrum would be, where a system would balance. Really the purpose of doing the one-dimensional case was to get this formula right here, which we use to extend to the two-dimensional case, which looks about like this that we solved last time. In the two-dimensional case, we have point masses. Sometimes we just call these particles of masses m1 through m3 at the following coordinates. And we calculate the moment about the y-axis to be m sub y in this way, where mi refers to the mass and xi refers to the first coordinate. Then, analogously, we divide the moment of the system about the x-axis to be this computation here. Any questions about that so far? Okay, so what we want to do next is figure out how in the world we're going to go from this discrete case of point masses to this continuous case where the mass has been smoothed out to a uniform density and uniform thickness. So that's what we're at. Any questions before we give this a try? Okay, so we're going to come up with a formula for the center of mass, and essentially those are the right formulas, m sub y and m sub x. Their interpretations are also exactly the same. Say, for example, if we look at m sub x involves the mass times the second coordinate, y, and the purpose of an m sub x, it tells us what the tendency is of the whole system to flip about or rotate about the x-axis specifically. So we need to calculate m sub x and m sub y in our current situation. Any questions then before we give it a try? Okay, so let's try this out. So our curve has been sketched, and the entire region is inside here between the x-axis, the curve, and the two vertical line segments. And if we want to calculate the centroid, which is a fancy name for center of mass, this is how we'll start. We once again partition the closed interval from A to B into n subintervals of width delta x is equal to b minus a divided by n. So it's the same kind of feature that we've seen in the derivation of section 8.1 on arc length, 8.2 on surface areas of revolution, and as well as centers of mass. The reason we have to do this is the whole chapter is on applications of integration. So by applications of integration, we're really trying to see how can we force a Riemann sum into the problem so that we get a particular definite integral. And this is always the start of defining those Riemann sums. So let's go and partition these intervals. So this will be a case where A is x naught. Let's partition like this. It might not be perfectly equal width, but that's okay. This will be x1, x2, x3, and x4. So this picture will be specific to n is equal to 4, but we know we're going to be taking a limit as n approaches infinity. So next thing we need to do is decide on a sample point on every one of the subintervals. But keep in mind, we are going to be building rectangles. So an arbitrary rectangle may look like this, and we need its center of mass. Essentially what I'm trying to do is take this continuous case where all of the mass has been spread out and make it be a point mass, much like the system up there. I can turn it into point masses. We'll take the limit as n goes to infinity and hopefully get the right formula. So upon partitioning from A to B into n subintervals of length delta x, this would be a particular rectangle. And if I want the center of mass of this thing, would you all agree it ought to be just the center of the rectangle? Yeah, I could look at halfway from here to here and put a vertical line that goes this way. So if I was trying to find a beam to bounce the entire rectangle under, that would do the job. And if I want to bounce under a single point, I'd go halfway from the bottom to the top. And right here would be its center of mass. So that's going to be really the punchline to how we get this done. So if we want to have the midpoint between the two subintervals, say xi to xi minus 1 to xi, the type of sample points we ought to take are just the midpoints. The midpoints will give us precisely what we want for the x coordinate at least. So after partitioning AB into n subintervals of width delta x, we'll take the sample points. We denote the sample points by xi star to say they could be anything. The sample points in the intervals xi minus 1 up to xi to be the midpoint xi bar. If we do that, we already have the first coordinate of the center of mass of every single rectangle that we've constructed. That's an efficient way to start. So let's put that on our sketch. Maybe we'll do it in red so it doesn't look too busy. So this would be the first midpoint at height here. So that gives us a rectangle that looks about like that for the first one. Then at second midpoint, our height is here. So now we have, this is a rectangle, and then so on down the line. So this one is a bit shorter. Then finally this midpoint increases the height of the very next rectangle. And that would be the view so far. So in this picture we have 4 rectangles. Each one of them is going to have a center of mass that we would like to calculate. So let's calculate them all immediately, all at once. Any questions so far with the derivation to this point? Okay, so this, just so that this picture doesn't get too busy, let me just grab an arbitrary rectangle out of the 4. So let's consider the height rectangle. Let me do a slightly better plot than this one. So I'm taking this whole picture, focusing on an arbitrary rectangle. It'll be between x sub I minus 1 up to x sub I. The midpoint is x bar, and the rectangle might look about like this. So just imagine any one of those 4 red rectangles there could be pulled out, and this is about the view you would see. The next thing we want to know is the height of this rectangle, which would correspond to the height of the point here, and that would be f at xi bar. So now we have the x coordinate of the centroid, but knowing the height of the rectangle tells us we'll just cut it in half and you'll have the y coordinate of the centroid or center of mass for this rectangle. So at 1/2 f at xi bar, we have this coordinate here, which would be the center of mass, which is the same kind of notion of the center of mass that we were looking at from before. Let's call this center of mass Ci for the ith center of mass, and the coordinates of Ci would be xi bar for the first coordinate. That should have been an xi down there, and the y coordinate should be 1/2 of f of xi bar. So we have now a whole bunch of centers of mass of the rectangles. So that's where we're at so far. Any questions to that step? So now what we're trying to do is we're regressing to the problem we ended on last class, where we had a system that looked much like that of point masses in a discrete layout. Once we calculate the center of mass of all the rectangles, say the first one would be here, C sub 1, second one slightly lower here, C sub 2, slightly lower again here, C sub 3, maybe barely higher, C sub 4. Then I'm visualizing the original plate as being a system of specifically these point masses here, here, and here. I want to imagine that that's all the masses that really matter, accumulated at those specific coordinates. If we do that, then we can in fact calculate, well, estimate the moment about the y-axis and the moment about the x-axis. They're not the correct moments just yet, but we're getting there. So any questions so far to that step? Okay, so at this stage, we're repeating the problem that we did last class, where we're only considering these masses here, and we can now estimate m sub y, where m sub y is going to be the moment about the y-axis, and by definition, it tells us we need to take a mass I. So it is going to be approximately equal to a summation as I goes from 1 to n. In our picture, n is just a measly 4, but it's going to become arbitrarily large in the limit. We take a mass times I times the first coordinate, x sub I. And all of these first coordinates x sub I in the formula are really the midpoints, x sub I bar. So that's our formula so far. The one thing we haven't considered just yet is the ith mass. It'd be the mass of the ith rectangle, and to get that mass, we can say mi for ith mass is going to be equal to the density multiplying the area. So that's our standard definition for the mass of that rectangle. We in fact have the density. At the very onset of the problem, we were told the density is rho. So we take the density of rho, mi is then rho times the area of the rectangle. The area of the rectangle would be the height, f of xi bar, multiplied by the length from xi minus 1 to xi, but that's precisely the length of the intervals, which were all equal to delta x. So the density is rho times f of x by xi bar times delta x, where this portion is the area. So we now have all the masses of all the rectangles that we would build in a configuration like this. If n gets very large, we'll have numerous different masses, but we're going to plug them all into this formula up here. This would then be equal to the summation as I goes from 1 to n of, we said that the ith mass is equal to the density times the area, which is f of xi bar times delta x, and parentheses just to say that quantity is from the mass, multiplied by xi. Xi refers to the first coordinate over here by formula, which is the midpoint, xi bar. So that's the formula for the moment about the y-axis. Similarly, let's calculate the moment about the x-axis. Any questions so far to that point? Okay, the problem is almost essentially done as soon as we have both moments. What's pretty cool about this problem is we're really just literally copying the same problem that we have done before, using the same formulas and the same physical interpretations. So we can say next, m sub x is the moment of the system about the x-axis. By the system we mean, remember, the original plate, which was this curve here. This figure is getting awfully busy. So we can say that this is, by formula, going to be approximately equal to a summation as I goes from 1 to n. Here we take the ith mass, m sub I, multiplied by the second coordinates, y sub I. So we already know the ith mass. We can fill that in to say that this is now equal to the summation as I goes from 1 to n of rho times f at x bar sub I times delta x. So that was our mass. Then this is communicating we have to multiply by the second coordinate of every single center of mass. So, and this center of mass for the arbitrary ith one, the second coordinate is a half of xi bar. So that's what goes outside over here. 1/2 f of x sub I bar, where bar is for midpoint. So now we have the approximate centers of mass. Any questions to that step so far? One thing that we might be predicting is going to be necessary down the line is that once we actually calculate the coordinates, the first coordinate and second coordinate of the centroid, or center of mass, we need lowercase m. But lowercase m just refers to the total mass of our plate. So if we know the density of the plate, and I know the area of the plate, it's going to essentially give me the total mass minus the thickness. Does that make sense so far? Okay, so we can say, just for the sake of simplifying computations, let's take the thickness to be a single unit. That way we don't have to fuss too much over the thickness, which shouldn't really enter into the derivation. So that's going to give us, next for total mass, a formula that looks like this. So m, which is the total mass, again, this is assuming the thickness of just a single unit. This is going to be the summation, or rather not quite the summation, it'll be the density again, multiplied by the area, A. By area A, we mean the total area under this curve, a white curve here generated by f of x, bounded between x equals a to x equals b and the y-axis. So this is our total mass formula, where A is the definite integral from a to b of f of x dx. So that's a wonderful formula. The total area is just an ordinary definite integral. If you multiply it by rho, we can say that that's the total mass. The questions so far about that? Okay, so now we're ready to say, if with this configuration, once we resolve this problem, where we're still approximating, we'll be able to say what the full formula is for both the x-coordinate, x bar, and the y-coordinate, y bar. In fact, that is the right formula, but our trouble is these approximations. If we can make these exact, we'll have the exact coordinates themselves. Any questions then so far? Okay, so what would you say is the missing step so far to make this a dead-on exact equality at this stage? Now, our approximation might not be too bad, but the trouble is, in our figures so far, n was 4. So it could be a horrible approximation. What could you do to make it better? Yeah, n needs to get large, but not just large, arbitrarily large, so that's the limit. Which means, if we take the limit of this as n goes to infinity, notice we have a delta x in the picture, that is literally now a Riemann sum. And that's what we mean by applications of integration. We'd like to take processes like finding centers of mass, extend it to a continuous case, but use limits of Riemann sums to get the precise formula. So finally, upon taking the limit as n goes to infinity, we could say m sub y is equal to limit n goes to infinity of the summation I goes from 1 to n. Let's rearrange this a little bit better. We can say maybe let rho come first. Let's take xi bar next. Then f of x bar should come right after. Really the one thing that you definitely want to write in a limit of Riemann sums is delta x ought to be the very last thing. So now that's a limit of a Riemann sum, which means we'll recall f was continuous. That automatically says the limit exists, and also that the limit can be found by taking, let's take the definite integral from a to b. Rho is just a constant, so we can pull it outside the definite integral. Then everything else copies as the sample point, which was a midpoint, just becomes x. So x times f of x. Delta x becomes the dx. So that already tells us what the moment about the y-axis is exactly equal to. It's just another definite integral. And notice in doing this problem, we're up to 2 integrals already. So when we do the moment about the x-axis, there's 3 integrals you would have to solve in each problem, unless you know something about the area or something about symmetry that cut the work down. Well, let's take another limit of this thing right here. We can say f sub x is equal to the limit as n goes to infinity, summation I goes from 1 to n. Then we have rho. Let's put that first, the constant. Next thing we can throw in there is, well, notice we have a constant of a half. We could pull that outside the limit if we'd like. We also have f of xi bar twice in multiplication, so we have to square it now. So it's a half f of x sub I bar squared, and the last portion is delta x. So that format now tells us what the definite integral must be. We can say that this is equal to, let's pull out rho once again, definite integral from a to b, and this looks kind of funny. The way the formula is traditionally written is with a half inside. Not because it has to be, but it reminds us that we found that moment about the x-axis by taking half of the function height. So it's reminding us about the derivation of the rectangle itself by leaving it inside. The f of xi squared is a little bit harder to explain. That seems like it came out of nowhere. That's just a consequence of taking the mass of the ith rectangle, which involved f of xi, and taking the second coordinate, which involved it once again, giving us a power 2, and delta x becomes a dx. So we have all the moments. Any questions so far? Okay, then the centroids are found by taking the moments, m sub y and m sub x, and dividing by the total mass m, so this quantity. So we finally have a formula for the x and y coordinate of the centroid. So let's state that next. We can say then the x and y coordinates, or coordinate, just one, of the centroid is x bar equals m sub y divided by total mass. So, same formula as before, but now we know m sub y is this thing. We're dividing by total mass, which involves density times area. So the density rho would cancel out, which is quite nice. It's interesting though, it's necessary for the derivation, but upon actually getting the formula for the x-coordinate, we'll have just 1 over the total area A, which is found through this formula, multiplying the definite integral from a to b of x, f of x, dx. So that's a nice cancellation to have. Then finally, we can say the y-coordinate is the moment about the x-axis divided by total mass. Similarly, it's the reciprocal of the area multiplied by definite integral from a to b, a half of f of x squared dx. So that's the full set of formulas. I would say this together with this will tell us specifically where to drop a point on this picture, maybe it's somewhere out here, to get the centroid x bar, y bar. So that's how we can take a continuous case, make it discrete, take particular limits using the prior formulas, and get our Riemann sums. Any questions about that so far? So it's kind of a neat process because it's really just all coming from the single dimensional case of trying to find the center of mass or the fulcrum where things would balance. Can extend all the way to center of mass in this case. Questions that come up a lot are, we insisted on uniform density and uniform thickness. If we break any one of those, particularly if we break uniform density, the problem we have is we just need to do multivariable calculus. So this is another great problem that would be revisited in Calculus 3. If certain regions of the plate have higher density, we need a different function to describe that. So it takes more work. But it's just an extension of what we've done so far. So if we take Calculus 3, it goes even farther. But what we should do next is, let's calculate some centroids. Any questions first before we do a calculation using these formulas? Okay, so let's go off to building our own plate and find the center of mass. Instead of calling it a plate, the book goes with lamina, which is just fine, but it's kind of a strange word. And this is the typical setup in a lot of these problems. It tells us to find the exact coordinates of the centroid for the region bounded by the following curves. So bounded by the curves which go as follows. First curve is equal to y is equal to e to the x. The next one is y is equal to 0, even though it's a straight line segment, a horizontal line segment, we'll still call it a curve. And the last ones are x equals 0 to x is equal to 1. So that's the full statement of the problem. And we know, unless we can exploit symmetry in a particular way, it involves 3 integrals. And this is the first one I would typically do in every single computation, because the next formulas involve that total area. So we're just going to start integrating. But one thing you really ought to do every single time you solve a problem like this, whether it be a homework or an exam, is eyeball it. We should actually sketch that region and just visually estimate where it should be. Then when we get the coordinates ourselves through computation, we can see how far or how close we are and possibly save ourselves from some errors. And again, if this were an exam problem, I would sketch the region so that you could do that same sort of thing. So let's start with a sketch. So the function y equals e to the x, I'd probably sketch first. This is essentially telling us the domain we're going to integrate from x is equal to 0 up to x is equal to 1. Then, well, let's maybe keep the scale the same. If I want to visually estimate areas, it might be handy to have a uniform scale for both x-axis and y-axis. So my sketch would start like this. Y equals e to the x starts at height 1 when x is 0, when x is 1, we're at height e itself, and e is about equal to 2.7. So we're going to end up at maybe about here. So at 1, we have this height at e, and the curve will look about like this. So we've sketched y equals e to the x just on the relevant domain from x is equal to 0 and x is equal to 1. X equals to 0 would be this curve. X equals 1 would be, this curve we kind of missed. Hang on, we can fix this. X is equal to 1 would be this curve right there, well, the segment of it. And y equals 0 is just referring to the horizontal x-axis. So once we take all those curves into account, we definitely have some bounded region R. And that's what we're looking for. Sometimes it might not be apparent what to highlight, but it should always be some region that's enclosed by the given curves. Next, if I was to visually estimate the coordinates of the centroid, I'd first probably look at halfway, 0.5, between 0 and 1. So there's more area to the right of a half, so I would say the x-coordinate is slightly off to the right. Would folks agree with that so far? Okay, then at 1 up to about 2.7, there seems to be much, much more area below. So I would say maybe it's possibly just barely below 1. I would visually estimate it to be here. I could be a good amount off, but if I'm way, way off, I'll know for sure and know that something's gone wrong in the calculation. So you don't have to be perfect when you visually estimate. So now let's get started and see how close we get. Questions so far? Okay, next thing we need to do is I need this total area that's been highlighted. So that's A from the formulas over there. But the total area is just a good old ordinary definite integral. They'll go from x is equal to 0 to x is equal to 1 of the function f of x. But we take this to be y is equal to f of x. So by the formula given for the total area, we're taking the definite integral from 0 to 1 of e to the x. The antiderivative is itself the best antiderivative ever, which we evaluate from 0 to 1, which becomes e to the power of 1 minus e to the power of 0. So this is a total area of e minus anything to power 0 other than 0 would be 1 itself. So 1 of 2 is down. Next we go off to, say, the x-coordinate of the centroid, x bar. Questions so far with the total area? Okay, once we have total area, we can say the x-coordinate of the centroid is reciprocal of total area, multiplying the definite integral from 0 to 1, and we take x times f of x. Our f of x would be this function here, so we're taking x times e to the x dx. Then this essentially becomes a review problem. We're back to section 7.1. To get that as an antiderivative, we need integration by parts. So we can start off by saying, when we do the integration by parts, u ought to be x. It's always an excellent choice because its differential simplifies to du is dx. That leaves up e to the x dx, or dv. The antiderivative of this differential equation would just be e to the x itself. So we can use that chart to rapidly get our antiderivative. So down below, we can say x bar is now equal to, if area is something like e minus 1 or worse, I usually just substitute in its value in the very final step, so I'm not carrying a huge thing. This is not too bad, but it gets worse, possibly. I don't want to carry that whole thing down the line, so let's just use 1 over a multiplies. We take x times e to the x, which can be evaluated from 0 to 1 immediately or later on, it's really your call, minus the antiderivative of e to the x times dx. Evaluated once again from 0 to 1. So that would be the full formula for x bar, and then the next part is halfway through the integration by parts. We just need to solve this antiderivative, which we have in fact done once, so we already know that that's going to be really e minus 1, and plug everything in. Does that make sense so far? Okay, so let's start evaluating. Next, we have x bar is the reciprocal of area multiplied by, I'll do this evaluation here next. So at 1, we have 1 times e to the 1. at 0, we have minus 0 times e to the 0. Then we've already done, well, not including the negative sign, we've already done this bit already. Definite integral from 0 to 1 of e to the x dx, evaluated to e minus 1. So we can say that this is going to be minus, copying that negative sign, e minus 1. Now we're just simplifying from here on out. So we can say, by substitution, the area itself is, again, e minus 1. That seems to be everywhere in this problem. Multiplying, here we have e, but then minus e. Or maybe let me take a couple steps to write it out. This is e, then we had 0, then we have minus e, then we have plus 1 through distribution. So it's just 1 times 1 over e minus 1. And if you stop right there, that would be completely fine. But in a problem like this, I'd really like to know what 1 over e minus 1 evaluates to. That comes out to about, let's see here, 1 over e minus 1 is about 0.58. That seems about right. We said that there's more mass to the right of the halfway mark, 0.5. So the x-coordinate of the center of mass should be slightly larger than a half. And we're seeing it in 1 over e minus 1. Any questions with that? Second half of the problem, or second third of the problem? Okay, so once we have the x-coordinate, we just switch gears and do another definite integral for the second coordinate, y bar. Here, we take the reciprocal of area once again and multiply by a half times the function squared. Let's maybe do that over here. We have that y bar is reciprocal of area, definite integral 0 to 1 of a half times the function, which is e to the x, to the power of 2. So that's the setup for the second coordinate. Then if I were to work that out, I'd probably pull the half out. It was just left in for physical interpretation of how the derivation went. Now it's the definite integral from 0 to 1. We multiply the exponents by the exponent laws to get e to the power of 2x dx. That's a slightly worse integral, but if you like, you could use a u substitution. Or because this is to the power 1, we could say that this evaluates to 1 over twice the area, multiplying antiderivative of an exponential with a power 1 would be itself. Then we need to account for the chain rule. In our check, if we multiply this by the derivative, it would be a 2 that comes out. There's no 2 here, so we throw in an extra 1/2, and that would be our full antiderivative, which must then be evaluated from 0 up to 1.